Okay. First of all, thanks for organizers, Arnolds, for inviting me here. So, I'm a space researcher from Swedish Institute of Space Physics. So, space research, it's not so much about photons. Mainly we are dealing with other things than photons. But this gave me a good opportunity to look in a different light on the things I'm doing. So, thank you very much. So, let's look a bit, start from a very large scale and then go down to the space research we are doing. So, if we take galaxy clusters, so if you take a space, so you have done the measurements of galaxy clusters, so there is a lot of galaxies here, some bigger galaxy in the center. You take the picture of the region, both in X-rays and optical. So optical, that's the blue color, X-rays, that's the red color. And now, astronomers, what they can do, they can weight the things. So they weight how much mass is in the all galaxies, and you can also weight how much mass is in the X-rays. Not in the X-rays. X-rays are coming from a plasma, so charged gas, which is filling the region between the galaxies, high energy electrons, protons, other heavier species. And now if you do this, comes the surprise that there is more matter in the plasma than in the visible matter that you have in the galaxies. So when you do this kind of weighting, you realize that if you take a universe, there is more baryonic matter in the plasma than in the, let's say, stars that we are observing. Of course, we all know that the dark matter is even heavier, yes? So this also you can see. So if we take something similar, galaxy clusters, which are colliding, so now it's a measurement in X-rays, so we know, oh, here is the most of the mass residing, visible mass. So when you can see two galaxy clusters colliding, so this is one, this is another, moving through each other, yes? So now if you take this picture, one can observe here is something like a shock, yes? So these two galaxy clusters, as they are colliding, they are breaking. Now, surprise comes that if you look on a mean free path, so how fast your particle, your charged proton, electron can move, it is much bigger than this sharp boundary. So there is forming a shock, but it is not due to collisions. So this kind of galaxies, when they collide, they stop due to some shock which is collisionless. So it kind of brings us to the topic that studying shocks, this is the largest shock one can observe in the universe, in some sense. So there is some other physics than just Coulomb collisions. So something more should come at plasma physics. Now if you look on this picture from a different point of view, the dark matter that we are having, that's not plasma. So if you take the same picture, so here are the colliding galaxy clusters, but if you take all the kind of your picture and try to estimate it from where is the, based on a lensing effect, you can see where is the total mass residing. Then you can realize the total mass is the blue parts here. So that's where your dark matter is. So when these two galaxy clusters have collided, the dark matter has continued without stopping, while our plasma, it has stopped due to these shocks between, yes. So that's where we have our plasma, our baryonic matter. So that brings us to the topic. It's important to study collisionless shocks in plasma. So if you look on what is a collisionless shock, let's start with a normal shock wave just in general. So if you have some source of waves, which is the rest frame propagating out with some velocity, so if you go to the moving frame, if your source is moving, if it's moving slower than the wave velocity, you will have waves propagating in all directions. If it's moving faster, you will have this very characteristic cone, shock cone. Depending on how fast your source is moving, the angle of the shock cone will be steeper or less steep. So here you have a shock, so your object should move with a velocity which is faster than the wave velocity. Then you have a shock. Of course, we have different examples of the shock. One nice example often has been shown, that's your airplanes, yes, when they are close to the Mach number 1, so just Mach number, that's the speed of your object divided by the wave speed characteristic. So when they are reaching over the shock, so when they're reaching over speeds which are above the sound speed, so you are forming a shock. So one can see here a very nice picture. You can have shock also, for example, this swimmer when it's swimming. So here the speed of the surface waves of the water, so the swimmer is already going slightly above, so you form a shock in front. Here is just a simulation of some Apollo capsule which is coming through the atmosphere, yes, so it's forming a shock in front of it. So there is a lot of examples of the normal shocks, and here usually collisions are playing the main role. So the thickness of the shock everywhere is defined by the collisions. Somebody who wants to make a shock, you can also make a shock with a ball whip. So that's, for example, also example of the supersonic boom. But what is happening in the plasma? So if you have a plasma, it should be some different effect which is breaking the plasma, because it cannot be collisions which are making shock. So this is a numerical simulation. So what you are having here is, here one sends in a plasma with a supersonic velocity. Now in a plasma there is a different kind of waves than the sound waves, so they are affected by the charged particles. But there are characteristic waves, and the speed of them is LV speed. So when you send in something with a flow speed which is much higher than LV speed, you have to form a shock. So what you are seeing here is a formation of the shock. So speed is coming in, and here it's breaking. This is a shock region. So why it's forming there? If you look on a mean free path, it is much bigger than this screen. So it has nothing to do with the collisions. What is happening is a collective effect. Collective effect of ions, electrons which are coming in here, which are creating a current, which is making a bigger magnetic field downstream. And at the same time, these particles are interacting with this magnetic field and gyrating and stopping at that region. So it's a collective effect where the plasma itself is generating stronger magnetic field, and the stronger magnetic field is affecting the plasma. And that's it. And then on a scale, which is a kinetic scale, which is a, let's say, typical scale is a gyro radius of an ion or electron in plasma, you have a stop. Your supersonic flow becomes subsonic. So it's more than LV speed, and now it's less than LV speed. If you look now in details, what particles are doing here, when they're coming, they're getting heated. So in the shocks, like the shocks that I'm showing, you can heat plasma up to millions of degrees. So it's really hot. Plasma is very hot. Not only that, you heat plasma to millions of degrees, but some of the particles you even accelerate to well above the thermal energies. So it means that if you look on some particle, what it is doing here. So here is just from a simulation. These are two different simulations, but it was easier for me to show the principle. So if you are in a shock frame, so you're all the time in a shock frame, and then look on some particle, what it is doing. So it will be some particles there. It's coming into the shock. Sometimes it's moving along the shock. So what is on the axis? This is the position, and this is the energy. So you look how your particle is gaining energy. The particle is coming into the shock, then it moves along the shock. It goes back and forth, again stays in the shock. So every time it's close to the shock, it gains some energy. Particles can gain also energy just going back and out. So they come in the downstream, in the upstream region, and by reflection they also can get energy. And in such a way, they can get very high energies. So you heat the plasma, so that would be you just thermalize it to millions of degrees, but you also can get particles which is very high energy. So if you look on the distribution function, how it looks like. So this is energy, this is differential intensity. So somewhere is a thermal component, and then you have a tails, power law tails. And as the particles get accelerated in the shocks, so these tails can go to higher and higher energies. And as I said before, yes, so here you can have millions of degrees. So plasmas that you are observing in the universe, it's very hot. Hundreds of million of degrees also can be. Okay. Let's go to cosmic rays and supernova remnants. So we had these galactic clusters colliding, but if you look on the very energetic particles, which are coming from the universe, so there is this energetic particle measurement. You go from 1 GeV up to 10 to the 20 eV, and these are the fluxes, so you see this very long tail. So what I was explaining about the shock acceleration, it contributes part to the cosmic rays up here. So one is believing that the shock acceleration is really generating some of the largest energy particles that we have in the universe, cosmic rays. So what one thinks is where it's happening is, at least large part of it, is at supernova. Also there we have a shock. So let's look again on some supernova. Again we look in with the photons, yes, because any astrophysical objects that we have very far, it's just photons which are bringing us information. But we want to tell something about what's happening there, what plasma is doing based on that. So this is a picture of supernova remnant in gamma, X-rays and optical. So what is supernova remnant? So star has blown up a few hundred years ago, and now we are observing, so there is still material coming out, including plasma. In this case, it's coming out with thousands of kilometers per second, and it's going into interstellar space. So it's forming a shock in front of it. It's the same way, it's a supersonic speed forming a shock. Now shock you can see here, very blue light, which is X-rays. In this case, X-rays, so that's a shock. It's a bit difficult to see, but that's where you have a shock. So where X-rays are coming from, this is electrons which are heated as a shock, and then there is synchrotron emission. So due to synchrotron emission, you observe X-rays. So by observing X-rays, you can tell how is electron spectra roughly doing at this shock. So we can try to tell something about what plasma is doing there. So we are observing in X-rays, but then we want to say what plasma is doing there. By gamma, this is something recent in the last few years, I think 2009 maybe. So one has observed also what ions are doing, but this is much more difficult to see. If you look on the cosmic rays, most of them are protons. So if you look on some kind of what they are doing, proton, then if you have some supernova blow, so proton will kind of do random walk, because there is magnetic fields in the galaxy, so it's kind of reflected off those magnetic fields, and it will come to the Earth from a random direction. So we can never know if this photon, this cosmic ray which is coming, is really coming from a supernova. So that's kind of challenge. The idea was suggested even like 60, 70 years ago, but you cannot test it. One way to test it is, again, photons, because if photon is coming to Earth from let's say, supernova, then you know that supernova is really the source of the cosmic ray. So you need some photon which is coming due to the protons, due to the cosmic ray. And here comes in the gamma. So if you have some proton very close to the supernova, and if there is a cosmic ray photon, so both are protons charged. So in the collision they can create a pion. And then this is now, you can see from, as it is decaying, you will form two gammas. So due to this process, when you observe gamma rays, and if you can locate where this gamma ray is coming from, you can see whether these protons, these accelerated protons, are really at the supernova remnant. And that's what has been done. So for example, using the Fermi telescope, looking in gamma rays, one has really tested this idea, and it has shown that indeed cosmic rays are accelerated at supernova. Now it's still not clear if it's a main source. Maybe there can be also other sources, but it's very clear that supernovas indeed is creating supernova shocks. Collisional shocks there are creating the cosmic rays. Okay, so we went from galaxy clusters, we go to the supernova, something very far. Let's go to the termination shock. And this is much closer in some sense. So this is looking on a solar system. And if you take a sun, then from the sun, there is all the time solar wind. Charged plasma continuously going away in all directions. If you look on the speed of the solar wind, it's around 400 kilometers per second, 300 up to 700. So it's supersonic. So when this speed is going into the interstellar medium, because it's supersonic, at the moment where it breaks, there will form a shock. And this is so-called termination shock. So in all directions, if you look around the solar system, so you have a termination shock. It's at the distance, if you look on a shock, it's roughly 100 AU, 100 astronomical units. So if you look on the material which is coming from the sun, it's breaking as a shock, and then when it stops, then it's blown away as a tailward, because you have all the time interstellar medium which is blowing on your solar system. And here we have interstellar medium. The boundary between interstellar medium and the material which is coming from the sun is called for kilovolts. And potentially we have also here a shock. This is not known. This is kind of open question. So where interstellar medium is coming and then breaking down and then going around the solar system. Now the one difference from this shock, from the previous shocks that I was showing, is that here we can go by the satellite. So now we have a Voyager 1 and Voyager 2 which have crossed termination shock. So we do not need to look now remotely by photons on this sphere, but we really can go and see what plasma is doing there. Okay? So this is really important difference. So now, going from photons, we can do in situ measurements. Go there, measure magnetic field, measure what particles are doing, how they are accelerated, all the properties of the plasma. if you look at the distance, this is just a logarithmic scale just to show where this is happening roughly. So if this is the Sun, Earth is at 1 AU, so then termination shock is roughly at 100 AU. So it takes almost 1 day for radio signal to propagate to the spacecraft. Yeah? So it's pretty far away. And then like Oort's cloud is even farther out, and this is the nearest star. Yes? Okay, so spacecraft which has crossed the termination shock are Voyager 1 and Voyager 2. And it's pretty impressive. They have been launched 77, yes. So this is what, 40 years ago? Almost 40 years ago? Still working. So this is experimental device which you build 77, no way you can change anything, and it's still working. And they're moving away, so Voyager 1, which was last launched second, but which is now farthest away, so it's leaving the solar system at 70 kilometers per second. And it takes like 18 hours for radio signal one way to propagate. Mission end will be something like in 10 years. It's because of the less and less power and because of propulsion, the hydrogens that you have in the spacecraft is not so much like. And now here they crossed the termination shock. 2004 Voyager 1 and 2007 Voyager 2. So both have crossed. And the instruments that they have cameras because they were flying past all the planets on the way. But now the main instruments which are working now are magnetic field, charged particles, plasma waves. So you look on those properties and then you can see what plasma is doing. Okay. So that's, let's look at the real data, how it looks like termination shock crossing. So this is Voyager 2 data from 2007. So let's look at this panel, maybe easiest. This is velocity. So here is the solar wind speed, 400 kilometers per second. And you can see as it's coming very high and then it drops down to 100 kilometers per second. So this region where you drop from 400 to 100 kilometers per second, that's your termination shock. That's where the things stop. If you look on the temperature of the plasma, it's low, relatively low, few thousand Kelvin maybe, and then it goes up to 100,000 degrees. So that's where your plasma is heating. Yes? So in the same way, one can look on the details what magnetic field is doing there. It's less clear, but there one can see also increase in magnetic field locally, and there can also one can see the increase in the plasma density. When it's stopping, how it's getting higher density. Okay? If one looks on particle acceleration, so we saw the heating, one can look also on particle acceleration. There's something called anomalous cosmic rays. So they are coming from this termination shock. They are accelerated there. So, and the spacecraft have observed them. Now, of course, there are some open questions. As soon as you make in situ measurement, some of your theories you had before you have to change. So there is some surprises. So it seems that not everything is really happening at the shock or surrounding the shock. It seems the turbulent region behind the shock is also very important for acceleration. But that's normal. This is we had a professor from Germany which was often saying this, that I mean, if astrophysicists could do only one in situ measurement in their objects they're studying, they would realize all their theories are wrong. Because it's, when you have these very far regions, you can make a lot of theories. So this is exactly what has happened crossing this termination shock. Now let's come even closer. So we have even a closer shock, and that's Earth's bow shock. That's near the Earth. It's really close. It's only 10 Earth radii away, like 60,000 kilometers. So you have the Sun, not so close to the Earth, this is not to the scale, but just as an idea. So you have solar wind blowing at 400 kilometers per second. Mach number is 2 to 20, it can vary. So it means it's 2 to 20 times faster than the speed in a plasma. And then you form a shock in front of the Earth. Earth's magnetic field is defending the Earth, and so plasma should go around, so there is forming a shock. Now the big difference is, this is relatively close to the Earth, so it means we can bring even more instruments there to study. Heavier instruments, better measurements, so we really can do the shock physics there in very, very great detail. So let's look how such a shock can look in numerical simulations. These are Vlasov simulations, so it means you model your plasma in a velocity space. Normally it's like a fluid in a normal space, but you can also do a fluid in a velocity space. So then you have in a phase space fluid, you do a very large simulation, which in recent years it has become possible to do really global simulations of the, let's say, Earth's bow shock. And then one notices a few surprising things. So this is a bow shock forming. So you have velocity blowing with 400 kilometers per second, and it's very different on both sides. And the difference is due to the magnetic field in the interstellar medium, in the solar wind. So this is the direction of solar wind magnetic field. So where the solar wind magnetic field is pointing into the shock, that's so-called quasi-parallel shock. There you have very turbulent environment, very turbulent shock. Where it's pointing parallel to the shock, that's quasi-perpendicular shock. That's very smooth shock. Now if you look on the particle acceleration, you realize that most of the acceleration is happening at the quasi-parallel shock. And this one can confirm also by numerical simulations. You can do different angles of the shock. So for example, here is a shock, quasi-perpendicular, quasi-parallel. You look how much particles you accelerate, so to really high energies, and you realize that quasi-parallel shock is really good accelerator of particles. So it means when you go out with a spacecraft, you can choose which kind of shock you're studying. You can go for the physics and study the acceleration mechanism. So if you have some spacecraft in some orbit going around the Earth, so it's moving very slowly, what normally is happening, velocity, dynamic pressure in the solar wind is changing all the time, so this shock will move across your spacecraft back and forth. And you will be able to study. Magnetic field is also not constant. It sometimes changes the direction. So sometimes where spacecraft is, it will be quasi-parallel, sometimes quasi-perpendicular. So you can study these situations with the spacecraft, okay? And now when you go and do measurements, so you can observe exactly what I was showing, this distribution functions. You can see the thermal distribution functions. You can see the tails, how accelerated particles are getting accelerated. So this is just in 3 positions of the shock, how different kind of ions are getting accelerated. Now if we talk about which kind of spacecraft are studying the shock near the Earth, so one important satellite which has done a lot of work recently, that's Cluster. It was launched in 2000. I myself have done a lot of work with Cluster, mainly not on shocks but on other topics. But one should realize that doing space research of the shock is really advantageous if you do it sense out here. And one important thing is this, so if you take a space, so as I said, it happens on a kinetic scales, on like gyro radius of the ion. If you look how big is the gyro radius, it can be 100 kilometers. So your experimental device is much smaller than the scales you're studying. So you can do distribution functions, fields, everything very easily. If you would try to do the same in the lab, no way. Your characteristic scale will be 1 millimeter or 1 centimeter. And you cannot make a device which is 1 millimeter, which can do distribution functions, magnetic fields, and electric fields, and so on. So space is really very good laboratory to do the studies. This is very important point. So these are just data from a cluster, from a bow shock crossing. So this is just to show how real data of the bow shock looks like. So this is a time, 2 hours. This is a magnetic field. Here is very calm, you are in solar wind. Here is very turbulent, you are in the downstream region of the shock. Here is plasma density, it's low, a few particles per cubic centimeter. As you cross the shock, it's high, but it's also fluctuating, it's very turbulent. And then here are the ions, the solar wind coming in, very cold, so it's, if you look on thermal spread, it's small, and then at the shock it's getting heated. Now during these few hours, magnetic field changes the direction. So here is quasi-parallel, here it was quasi-perpendicular, and you can see it's more turbulent quasi-parallel, less turbulent quasi-perpendicular. If you look at the highest energies, so here is the energy, so here is the highest energy side. Where you have quasi-parallel, more acceleration, quasi-perpendicular, no acceleration of high particles. So you can study these things, mechanisms in the detail. Now we can go back to the supernova. If you measure supernova now in radio waves, so this is something like 1.5, 1.4, I think, gigahertz, around that. You can look at what is the orientation of magnetic field in the supernova remnant. So this shows the degrees. So here, your orientation of magnetic field is from the center out. And here, it's like 90 degrees, so it's perpendicular to the line towards the center of supernova. So what you're having situation is, this is a quasi-parallel shock forming, and this is quasi-perpendicular. And the radio emissions that you're observing here, this is telling you how much particles are accelerated there. So we see the same effect also in supernovas. So where you have quasi-parallel shock, you get a lot of acceleration, quasi-perpendicular shock, less acceleration. So by studying the Earth's bow shock in details, we can better understand also how things are happening in the supernova. So when you talk about such shocks, you have planetary bow shocks at all planets. So if you have a dipole, you will have a shock. So we have observed that Mercury, Earth, Saturn, Jupiter, So shocks have been observed everywhere. And it's interesting to study them because if you look on a solar wind, how high is a Mach number? So even though it's blowing all the time, it's 400 kilometers per second. Mach number is increasing with the distance from the sun. So you can, by looking on a Jupiter shock, you are in a different regime of the shock. So you can see the properties of the shock. So this is just an example of crossing the Saturn bow shock. So just maybe magnetic field if one looks. So this is solar wind magnetic field, you cross the shock, you see fluctuations. So one can observe these several crossings of the bow shock at the Saturn. High Mach number, so comparing Saturn with Earth, one has discovered, for example, how at high Mach number electrons are accelerated much more efficiently at quasi-parallel shock. Okay, if one looks about the future study, so one very interesting thing for studying shocks now is MMS. So it's a very recent NASA satellite which was launched. So Cluster was launched 2000, MMS was launched just a month ago, a bit more. So these are 4 spacecraft, very similar to Cluster, but now they're going down to the electron scales. The focus of the mission is the reconnection, it's a different process, but it will also do the shock physics. And it will allow to study really shock physics down to electron scale, so really understanding how electrons are accelerated at shock. If one looks a bit further in the future, there is, for example, Solar Orbiter project. I myself am involved in this project. So it will be launched 2018, so around 2020, we will start to make observations. And then one of the very important topics of this mission is studying the shocks which is due to coronal mass ejections. That sometimes sun is emitting a lot of mass, and in front of this kind of big bubble of the mass there is forming a shocks. And this is generating solar energetic particles which also affect, let's say, space weather on the Earth. So that's kind of in a 10-year perspective. If you go even in a further perspective, then just a few days ago we were at ESA trying to convince that we need a new mission that would go, if you look on an orbit, so that it tangentially is very close to the shock, so we can spend very long time at the shock and really study what is going there and resolve particles down to the kind of smallest scale. So current missions they're kind of averaging particle measurements over larger scales, so we want some mission which is really going down to the smallest scales where much of the heating and acceleration is happening. So this is kind of our proposal for the mission, and in 1 month we will know what is happening. So I didn't touch on one thing, but maybe I should just say that the shocks you can also generate in a laboratory. So there is also laser experiments doing these collisionless shocks. But unfortunately, a bit due to the lack of time, I did not put in a few slides. But this is also a very interesting topic and very hot, and there is a lot of things going on. So, okay, thank you very much. Yeah.